All right, this next bit of our course is going to focus on covalent bonding, and this is probably more detailed than you want to know, but this is what we got to talk about, so let's do it. Um, what I want to get into today with this one is start us off as like an introduction to covalent bonds, as before we start peeling layers and diving into detail. Um, I want us to remember that the octet rule is still kind of there. Maybe think of it more as like the octet loose guideline than rule. Um, but what was I saying? Oh yeah, remember gain, lose, or share. Things just fell off my desk. Gain, lose, or share electrons in order to get a noble gas configuration, and this is the most stable, lowest energy possible situation. I say loose guideline because as we keep going through some stuff, we're going to see a lot of things that don't necessarily obey the octet rule. Um, all right, so we're going to start off in a nice spot of single bonds. When we're talking about bonding, we're going to be drawing a lot of pictures in this too. So let's think of this. If we have a hydrogen atom with one valence electron, remember you can figure out valence electrons based off of the group A or B number in the periodic table. Okay. Uh, we have an oxygen atom with 6 valence electrons. These guys can share here, right? Um, but the oxygen still has an unpaired electron. It needs to share some more. It can find another hydrogen like this dude, and they can share here. Okay, doing this makes a water molecule. We could draw this two ways. This way is not as nice, but it kind of reinforces the idea that we have 2 electrons in these bonds here. Um, we can also draw it this way, where the bonding electrons are shown as dashes. Okay, we'll use the dashes most often because that's the normal convention and the way to do things. I just want to point out here, there's this picture here is good for 2 good things. One of those is it'll show us the bonding electrons. Let's get a bonding color, right? These would be bonding electrons. These are the electrons that are shared between the atoms that are covalently bound together. The other electrons are called non-bonding electrons. I should probably label these as well. Okay, these are non-bonding. They're only associated with the oxygen in the center of this dude. Um, and we often refer to these as lone pairs. Okay, and these red ones, I'll just put it here for completion. These red guys are bonding. Okay, we can look at another example. Remember we talked about diatomic elements. Chlorine is one of those things. Remember chlorine in group 7A has 7 valence electrons. So there's a chlorine atom. And the reason chlorine and all the other halogens exist as diatomics is because they have 7 valence electrons and they really, really, really want to have 8. So they're going to share those 2 unpaired electrons and make a chlorine molecule. That looks like this. This way, both atoms involved can claim 8 valence electrons. Those 2 in the middle are going to be shared equally between the 2 chlorines. Okay, all of these things we're going to classify as single bonds because in a single bond we're having 2 electrons that are shared. Okay, um, if we want to, we can get into multiple bonds, which will show up all the time as we see stuff. Remember we talked about diatomics again. Oxygen is a diatomic, and you can kind of get an idea of that. Remember, oxygen is group 6 again, so 6 valence electrons on this guy, 6 valence electrons on this one. Okay, and you'll notice here each oxygen has 2 unpaired electrons, and so each electron can form a bond with the other unpaired electron. So we'll end up forming 2 new bonds, or 2 bonds in between the 2 oxygen atoms. And we'll draw this like this. This is called a double bond. Those electrons look dumb. Okay, there we go. Um, right? We could also see this with something like ethylene. We can put together bigger things the same method that we've been doing for this before. I don't want to run out of room here. Ethylene has C2H4, so there's 4 hydrogens, 2 carbons. All right, remember each hydrogen has 1 electron. Each carbon has 4 valence electrons. So the mess looks like this, and we can put this together, forming single bonds and a double bond between the 2 carbons, right? Because if we compare right, we can put a hydrogen with this one, we compare a hydrogen with that one, we compare a hydrogen here and a hydrogen here, then there's still 2 sets of unpaired electrons on the carbon, so we can pair these guys on the top, these guys in the middle, and connect them all together and make it look nice with lines and say that we have an ethylene. We don't need to know the name, but okay. Those are good examples of double bonds. We'll see some other stuff as we do things. Let's talk triple bonds for a sec. Nitrogen is great for triples. Um, nitrogen has 5 valence electrons. So you can already see where we're going here, hopefully with this, right? Each nitrogen has 3 unpaired electrons. So when they come together, we can pair up all 3 unpaired electrons, right? So in the triple bond here, remember we're sharing now 6 electrons. Right, I didn't write it up here. In our double bond, we're sharing 4. I can't spell. I'm getting close to my little Zoom thing, so there we go. Okay, right. If we want to look at an organic example, we can try acetylene. Acetylene is C2H2, so 2 hydrogens and 2 carbons. Each carbon, I don't want to draw, oh, because I have text that's going to pop up in a second. Okay, so I've drawn this not in a good way. Right, again, each hydrogen can grab 1 electron from the carbons, right? So this and this, and then each carbon has 3 unpaired electrons, which lines it up perfectly for a triple bond. So acetylene would look like this. And they're all triple bonds, they're all sharing 6 electrons when we do that. Okay. What we've been drawing are called Lewis structures. This is one way to do it, and this works great if you have atoms in the second row where everything is obeying the rules, and it makes a little bit of sense, right? Where you can draw the valence electron dots and kind of pair up the unpaired ones to do that. It's a little slow and time consuming, and so later on we'll get a different way to work through that. But the Lewis structure is just a 2D picture of how the atoms are joined together to make the compound. I also want to put a note out in here, oh shoot, and say that carbon will almost, for everything we're going to see in Gen Chem, carbon's going to form 4 bonds, except if we have carbon monoxide. CO has a triple bond, so we could have used this for triple bonds. And in this case, each end of this has a lone pair. But this is the only case where we're going to see carbon with a lone pair. Okay. In every other scenario, carbon will have 4 bonds. That's not a B. Okay. Let's see, what else we got now? All right, let's talk bond length and bond strength as we think about this. Multiple bonds are shorter and stronger than single bonds. And we're going to think about this from the same way we thought about our trend of atomic radius and ionic radius and all these trends, right? Okay, so if your 2 atoms are sharing more electrons, it makes a stronger bond, right? And if they're bonding stronger, they are closer together. And because they're closer together, it's a shorter bond. So these kind of things go together. I want us to kind of remember this little mantra that things that are stronger are shorter. Okay. And what we mean by stronger is we mean in terms of bond energy. Call this the bond dissociation energy, or the BDE, right? This is the energy that you have to put into that bond to get it to break into its two neutral atoms. Okay. The higher the bond dissociation energy, this means the more energy you have to put into that bond to get it to break, the stronger that bond is. So, right. So if we look, here's 3 CO bonds, right? This single, this is bond length, dang it. The single is long, the double is shorter, and the triple is even shorter. And we can correlate this to the bond dissociation energy. I really should have put bond dissociation energy on here, but I didn't think about it. Okay. There's no need to memorize the lengths or anything like that, but the trend is going to be true here. Here's 3 nitrogen ones. The single is long, the double is in the middle, and the triple is shortest. Okay. And so we can say that the triple is going to be a stronger bond. It's going to have a higher bond association energy because of all of these things. One good tool we can use to tie all these things together is this idea of a bond order. Okay. The bond order tells us the number of pairs of electrons that are shared in the connection. Okay. So all we're doing is we're going to count the number of lines in your good Lewis structure. So if you have a good Lewis structure, you can count the lines in the Lewis structure and come up with the bond order, right? So here we have one bond, one line in the fluorine molecule. That's a single bond. That's a bond order of 1. 2 lines is a double bond. That's a bond order of 2. 3 lines is a triple bond. That's a bond order of 3. Okay. And so we'll be revisiting bond order as we do stuff. The nice thing about bond order is it lets us think about relative lengths and strengths. So theoretically, ideally, the fluorine bond here should be longest of these 3, and the nitrogen bond should be the shortest, which would imply that the nitrogen one is the strongest and the fluorine one is the weakest. Okay, because the atoms are different, this might not be exactly true, but I think it should be. Okay, so you can always count the lines in your Lewis structure to come up with the bond order. So once we get into bigger things, you can look at a bigger thing and look at it and count all the lines and say, oh, that's a bond order of 3. This is a bond order of 2, and every bond should have its own unique bond order with it. Let's look at these examples. Let's figure out what the bond order is for each of these, and then we can kind of think about what the ranking them in terms of bond length and bond strength. Okay, we're looking and focusing in on the CN bond, right? So this is a double bond with 2 lines. So this is a bond order of 2. This CN bond has 3 lines. This is a triple. This is a bond order of 3. And then your CN bond over here only has 1 line. This is a single, so that has a bond order of 1. So these numbers I've written here are a bond order. Okay. Once we know what the bond order is, we can compare the length and the strength of these. Okay. I want you to think about it a little bit before I write it down, but which one of these would you consider the longest bond and which one would you consider the shortest bond? Okay. Well, the longest of these 3 should be the single CN with the bond order of 1. The shortest should be the triple with the bond order of 3. And again, we can use the length. Ooh, crap. What did I do? There we go. We can use the, sorry, the length to correlate to the strength as well. Remember, the longest should be the weakest, and the shortest should be the strongest. Poor double bond gets left out in the middle and doesn't know how to spell. Okay. Another way to say the strongest is this has the highest bond dissociation energy, whereas the single bond here, the bond order of 1, has the lowest bond dissociation energy. So you're going to need to be able to compare bond order, figure out bond order, compare bonds based on their length and their strength depending on their bond order, draw some simple Lewis structures, identify doubles and triples and all that kind of stuff. And then we're going to make it a little bit more complicated in a bit, but we can handle it. Okay. Um, I'll see you in the next one.